correct one to use. Now, in actual fact, you don't normally work out the standard deviation yourself. You stick it in Excel and it does it all for you. Okay? But when you look in Excel, you'll find standard P. I think there's a P. I think there's a standard S or something. There are different ones. And the trick is to understand which one you should be using. And unless you've got the whole population, and you've got a population mean, which you normally haven't got, you should really use this version for the standard deviation, because you don't have a population mean, you're estimating the population. You don't know what the population mean is, okay? Now, you can have a little bit of fun working that out, why it's the case. There's a nice mathematical play around to work out why it's the case. And how you do that is you imagine that you've got just three things, right? You've got three things, and you are picking from three things effectively. So there are three choices, and out of these three choices, maybe this is like 0, 1, 2. Okay, 3 points. I won't go on too much about this. But basically, out of this set, you could pick up 0 and 1. You could pick up 0 and 2. Got the idea? You can pick up 1 and 2. And basically, you can have different samples. And the trick is that the average of all the sample standard deviation should have equal the standard deviation for the population. And you can have a go working this out, and you will find that you have to put n-1. Now, it's really beyond the scope. We don't need to worry about that. What we do need to worry about is that if we use n-1 here, when we do Pearson's and things, we have to use n-1 there. So the rule in statistics is, if you've applied an n-1 to your standard deviation, apply it in the next stage. Right? You don't need to worry all about the maths. Feel free to look it up, Google it, it's good fun. But the rule is, if you've applied it there, you have to apply it later on. So our Pearson thing, let's get it here, will be R equals 1 over n-1, okay, the sum of, and then we've got xi minus bar x over s dx times by, that's times yi minus y, mean over s dy. And this is how we work out the Pearson coefficient, okay? So what this is doing here then, we would work out for each of these x's, okay? We would take away the mean, divide by the standard deviation, that's the standardised thing, the thing we were talking about just before, and then we literally just multiply those together, okay? Now, because this little formula here, the way that we standardise data, okay? When we standardise data, there's a certain size that our data will never get bigger than, because we're standardising it, okay? And in actual fact, that data will never get bigger than 1, which is quite key. Okay, so this standardised data will be a tiny size once we've done that there, and this will also be a tiny size. So when we multiply those two things together, if you think about it, right, we'll either get a whole 1, if they're the same, and they're 1s, or we'll get something otherwise, we'll get some sort of number. We'll get a number that represents a relationship between them, okay? And what the Pearson test is doing is it's working out the relationship between each set of points. So that's why it's called product moment, because it's a product, it's multiplication here. Right, this is the product of the correlation. Okay? So it's doing that for each pair. And the interesting thing about this, I did actually make a note about this, it was kind of cool. Yeah, the interesting thing about this is that this number, if everything's going up really tidily, like 0.7, 0.7, 0.2, 0.2, 4.1, 0.7, 0.75, 0.75, then all those multiplications, every time you multiply 0.7 by 0.7, or even negative 0.7 by negative 0.7, they're always going to be positive. So the neat thing here is if the numbers are all the same, you always end up with this really nice positive thing going on. And it gets a big number, because when you average all those, you'll get a big number, because they're all positive. If there's a lot of variation where some things are going down, where others are going up, then these two numbers, one will be a negative number, because it'll be below its mean. You get me? So the ones here that are below the mean, on this one, that's below the mean, so when that's standardised, that will be negative, because it's below its mean, okay? Now, so long as the one over here is below its mean, now that one isn't. That one is above its mean, so that will be positive. And that has a bad on the correlation. Because it will give you a negative number that in this summation. In other words, it will drop the total R down. Does that make sense? Does it start to make a bit of sense that? So here, 6 and 30, that's above the mean, so that will be positive. This is above the mean, so that will be positive. So that will give you a positive number in this summation of things. So, you know, the positives are what you're looking for. Even if 2 are below the mean, like these two here, that's below the mean, that's below the mean, so they'll be negative numbers, and they're multiplied to make a positive number. So the deal is, what it's looking for is, are the things below the mean in both cases? The things above the mean in both cases. Pretty much if that's happening, then you're getting this stronger number. Once you get things messing around that point, that's where the negatives come in. So that's how the Pearson test works. Relatively neat. You end up with a number between 1 and -1. That's all you get at the end. You divide by n minus 1 if you've used n minus 1 in these. Okay? In those standard deviations. If you've used n in those, you should put an n in here. Okay? It's a matter of, it's almost fashion, but the deal is you have to do the same thing with your ends. You can't mess around picking and choosing what you do with these ends. You can have a go working this out. It's not rocket science to work out. We'd have to mess around with the calculator. We've got the other one to do yet. But the deal is you can, I hope you can understand this bit here, is that this one, you know, this is going to add a negative to the summation, so it drops the number. Okay? This one will add a positive to the summation, so that will rise the number. And the smaller that these numbers are, clearly, the numbers between these, the smaller they are when they multiply, then the more difficult it is to prove a correlation in either way or the other. There can be a negative correlation, or there can be a positive correlation. That's not a problem. As I said before, you can't use it really with 5 anyway, because that's just a nonsense. So be it. But that's with real numbers. That's the Pearson test. Gosh, the germs do like mud. It's sometimes called the Pearson product moment test. There is another way to work it out. I'll give you the other calculation, because this is kind of a fun calculation. I can go sum of xy minus sum of the x's times by sum of the y's. And this is actually easy to work out, because I have to mess around with the standard deviations, quite the same, divided by n, all over, wait for it, it's scary, square root of sum of the x squareds minus sum of the x squareds over n times by sum of the y squareds minus sum of the y squareds over n, over there. And you can use that, there's no standard deviations in there, right? And you can work it all out doing these columns. So you can start with your x's, start with your y's, do your x squareds, do your y squareds, and you can do all this without having any standard deviations in it. Now the reason that works is because you can actually multiply out this equation and end up with that formula, okay? It's just another way of doing it. But you would never do it by hand. There wouldn't be any real point. What you need to be aware of is that almost every statistical test has multiple versions of itself. So there's lots of different formulas. It doesn't mean they're wrong, they're just different interpretations of them. Because clearly here, that standard deviation, right, remember that can be calculated by knowing the x's and the mean. So you know, everything can come out to the same numbers effectively. So you don't need to, and the mean can be calculated just by adding the x's and having n. So everything should be able to reduce to the x's and the n's. Does that make sense? It's just a mathematical jiggle and pokery. So here, we don't need to worry about the means or anything. We just do all the numbers because we're doing the same thing. Okay? So that's worth having. But probably you're never going to use it to gauge. So that's Pearson's correlation. Are you happy with that idea that you can reduce it all to those? Are you happy with the idea? You don't have to be able to do it. Are you happy with the idea? The idea is that what we've got here, we've got averages, means, and these are done by sums of x's divided by n's. Yeah? We've got standard deviations, which are to do with sums of x's divided by n's taking away x's. So these are still x's take away sums of x's divided by n's. Everything reduces down to x's and n's and y's. Right? We only have standard deviations and things in between, because they make they make mathematical sense as concepts. The idea of standard deviation makes sense as a concept. This equation means no sense to anyone. No one knows what's going on. That's not great, is it? This actually seems to make more sense because it's saying, oh, we take the number, we take away the mean, divide by the standard deviation. And then we multiply by the other number, take away its mean, divide by the standard deviation. Two standardised numbers multiplied together, and we can make sense of that, can't we? We can't make sense of that, but actually you can do that by hand. Very easily, because you haven't got all this messing around here, having to square root 2, divide it into all these things, you get it? It's pretty gruesome, that's why we've not gone any further. Whereas on the bit on the left-hand side there, you can actually work it out without worrying about that. But that's not to encourage you to work these things out. Just stick them in a spreadsheet and then you get the answer. Okay, so that's Pearson. Actually, Pearson was the second guy to do this. There was another guy, a bit before Pearson, who kind of really invented this and just didn't get his name on it. Bit of a shame. There you go. And what you'll find, if you look up these tests, you'll find all sorts of strange things that go on. There's like a Fisher test that enables you to see if the correlation was robust or not, and there's all these extra bits and pieces to mess around with. But you don't need to worry about them. What you're doing, that will do. Right, so we'll have, let me check I've not missed anything here. Yeah, that's okay. Yeah, okay, so Spearman's rho. There's one thing I've mentioned there, which I probably should tell you. The actual value of R, that goes from -1 to 1, is this correlation number, just so that you know. If it's 0.8, 0.8 is not... Oh, why did you do that? 0.8, just so you know, is not equal to 2 times 0.4. Because in actual fact, the R statistic is not linear. Okay? If you notice, we're getting out to squares and all that kind of thing. So in order to look at the linear effect, in other words, is it twice as correlated as something else? Does that make sense? Then we have to actually refer to R squared. So we look at R squared. R squared is linear, all right, but R itself is not linear. So a correlation of 0.8 is not twice as correlated as a correlation of 0.4. Okay, what you do there is you do 0.4 squared is 0.16, 0.8 squared is 0.64. And what you actually find is that this one is pretty much 4 times as correlated as the 0.4. Okay? So that's kind of important. You'd never write that down. You'd never say, oh gosh, this data is more correlated. No. This data is 0.8, so that's well better than 0.4. But it's important to notice that means, because what it does mean is that 0.9 is quite a lot bigger than 0.8 in terms of correlation, whereas 0.5 is a little less bigger than 0.4. Do you get me? Because the gaps are not the same, because it's not a linear function. So that's worth knowing, all right? You wouldn't normally think that anything that was much less than 0.7 was anywhere near a correlation, really. 0.7 is a good cut-off for claiming a correlation. But again, that depends how many things you've got, because like I said before, if you only have 5 things, if you have 0.7, you've got a 20% chance of it being something outside, so it's a bit messy. Okay, so Spearman's. So Spearman, bless him, a bit easier, because it's all rank data. Let's get an example of this one somewhere. Here we go. Yeah, Spearman's rho. So Spearman is the pure relation, right? This is the pure relation. So this is when you've got deficit data again, tragic data. And it's typically when you've got data from something like a Likert scale. So let's get some data in here. So we've got A, B, C, D, E. Again, it doesn't make much sense with 5 things, but 2, 1, 3, 4, 3, 22, 34, 36, 49, 42. So imagine that we've got this data, and this data is not nice ratio data. So in other words, we don't know what these things really mean. they're just numbers, the scores. They might be scores on a Likert scale. So it could well be, is for example, happiness on a fun sort of scale, where 5 is happy and 1 is not very happy at all, really a bit sad. Does that correlate with, for example, scores on a maths test? So that's sort of interesting thing you might want to look at. You might want to say, oh, does the happiness on a Likert scale correlate with a good maths score? You know, if our students say, I'm happy at university, how does that correlate with the scores they get at the end? So in this case, it could be that one of your pieces of data is proper, right? This could be proper data, this could be tragic data. You've got to treat it all as tragic data then. You can't suddenly think, oh, okay, well, we'll have Rita Marriott and we'll go for tragic poor. Right, you've got to treat it all as tragic, right? So whether it's one piece tragic or the other piece not tragic, you've got to treat it all as tragic if you've got tragic data. And here we do that rank thing again that we did last week. So we rank the x's and we rank the y's. Okay, like we did last week. Put these in because I've already done them once. So if we have, it doesn't matter which way around we go, but we'll start with that as 1. So then we've got 2, it would be 2. And we've got 2 3s, so they would be 3, 4, and then that would be 5. But these two are both 3s, so they become 3.5s, yeah? Happy with that from last week? How we rank them? So we've got 2, 1, 3.5, 5, 3.5, I think. 2, 1, 3.5, 5, 3.5, yeah. And then we rank the other ones. So taking the same, now the deal with the ranking here, you can start at the bottom or you can start at the top, doesn't matter. Again, you could do the same thing on both columns, clearly, or else that's kind of rubbish. Right? So here we start with a little list there, so we'll start with a little list here. So there's 1, 2, 3, 4, 5, isn't it? 1, 2, 3, 4, 5. Agreed? There are ranks for them. And then we'll get our ranks and we work out the differences between the ranks. So differences between the ranks. Okay, so we do 2 minus 1, which is 1. Alright. 1 minus 2 is minus 1, 3.5 minus 3 is 0.5, 5 minus 5 is 0, 3.5 minus 4 is negative 0.5. Okay, so our differences ranks. Then you can guess what we're going to do next. We're going to square these. Okay, so we'll get 1, 1, 0.25, 0, 0.25. So then our differences in. Now what this is doing, what Spearman's is doing, is it's testing if the things are going up in the same rank order. That's all it's doing. So it's saying, is the third person on the happiness going to be roughly the third person on the maths test? Is the fourth person on happiness going to be the fourth person on maths test? Makes sense, doesn't it? The fifth person on happiness going to be the fifth person on maths test. Okay? And if they were all exactly the same, if these were 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, right, then we'd have 1 second 1 is 0, 0, 0, 0, 0 all the way down there. Yeah? They're all exactly the same. If the ranks were exactly aligned, we'd have a set of zeros, yeah? In that place. They're not exactly aligned, so we've got some numbers. So you can see that the bigger that this ends up, the slightly less correlated the data is. Agreed? Because if we had like a 1 and a 5, and a 5 and a 1 here, we'd have had a couple of 4s here, and that'd have given us some 16s up here. We've got some big numbers. Okay? So the bigger the number here, right? So this gives you a hint of correlation. Sounds like a perfume, doesn't it? A hint of correlation. Yeah. Made by Spearman as well. Yeah. So the hint of correlation, right? So this is bigger these, less correlation. Yeah. Bigger these implies less correlation. And then you actually do a statistical count up, so we add all these up. So some of these makes 1, 2, 2.5. Yeah? Some of the D squareds equals 2.5, so we add all those up. That is our key number, that 2.5. And there's this really bonkers formula, which I'll give you because it is bonkers. which is 1 minus 6 times, it's always a difference this word, all over right, yes, I've got that one in there, yeah. Okay. All over n cubed minus n. Now you sometimes see this as 1 minus 6 times sum of d squared. They often don't put the times in maths. And you might see here n squared minus 1. That's clearly the same thing. Those of you who can't remember how to factorise, you'll know that n times n squared is n cubed, and n times 1 minus 1 is n. So it's the same thing. It's the same thing here, right? And that 6 is quite interesting. The 6 is just there. That is it. The 6 is there. That is what is used for 6. Nothing to do with anything else. It's always 6. Right? It's always 6. Just get over it. It's always 6. So it's nothing to do with any of these numbers. The 6 is a firm number. You know, it belongs there. The 6 is to die for. Happy 6. Always 6. So then when we work all that out, we get our little numbers here. You can see this is dead easy to calculate. So we've got the sum of the d squared is 2.5. So we'd have 1 minus 6 times 2.5 all over n cubed. What's n cubed? How many numbers have we got, guys?
5.
5. So what's 5 cubed?
125.
125. Well done. Minus n, which is 5. So we've got 1. 6 times 2.5 is
15.
15.